Because I don't want to just spend less time in coordinate system, but I want to dig a little bit deeper. That, yeah, you said that we have this coordinate system to track our quantities in space, because there are various quantities which are direction dependent. So the question arises that, is this only Eulerian coordinate system exist, or are there some other coordinate systems also there? Well, so to understand this Eulerian coordinate, we have used this symmetry. Why this is symmetry? We use cube, and cube has symmetry because its length, maybe A, B and C, are same. Okay, well, it cannot be same, it may not be same, maybe it's cuboid and so on, but the thing is that, yeah, we are taking it as inspiration from cube, and it has some symmetry over length, height and height and breadth. Okay, well, can we construct some different symmetries? Well, we see too many things. Like, for an example, we have this circle here, over here. Now if you rotate this circle, and it will stay same. Okay, now if you use this kind of coordinate symmetry, where you are using this circular kind of thing, and this circle possesses the two-dimensional space, there is no any z quantity, so we are assuming that the thickness is really infinitesimal, that we can neglect this z-axis. So we are having x and y, and we are using this circular symmetry. So this way we can have two things, because in circle, the representation of circle, it's having radius and also how much angle it is moving. Okay, so radius means that how it is big, is it growing big or not, or how this angle is actually moving. So it's increasing, the theta is increasing or theta is decreasing, this depends. Therefore, so in space, in also Eulerian space and two-dimensional space, if we have some kind of object which has this circular symmetry, we can use this polar coordinate system. So polar coordinate system is just represented by these guys here. These are r, maybe its origin, and there are some kind of thetas and so on. So these are theta. So the polar coordinate had two parameters, which is my r and theta. Okay, now what are the unit vectors? The unit vectors are very simple. It has two quantities only, r and theta. So this is r hat, your unit vector, so it is increasing the direction in this way. Okay, if your radial vector, it is called radial vector, if your radial vector only can increase this way, or it can shrink or expand, so this is called r hat. And the theta hat is increasing direction in theta, because this angle which is making with this x-axis, that is theta, so theta can go this way. So we are perpendicular from this thing, this represents this theta hat, and this represents your r hat. So theta hat, whenever I'm saying it, it's a handle, and how you can increase from this handle is theta all the way to 0 to 2 pi. So these are the two quantities which is represented by here. Now if you have some any kind of vector in polar coordinate system, now you can write it here, not in ax term but ar term, r hat, and plus a of theta term in theta hat. So what are the vectors in terms of how much is radially there, and what are the angles involved in theta? And this way we can have this polar coordinate system. Now, okay, we have polar coordinate system, and mind it, it's in two-dimensional thing. So we see three-dimensional, maybe one-dimensional when we are talking about the simple x. If you have two-dimension, x and y, okay, and if we have this z is involved, z dimension is involved, then we have this three-dimensional thing. And we are studying this xy, where we have this symmetry involved, where we take this circular kind of symmetry, and we got this polar coordinate system, which is represented by r and theta. Let's move further, and can we extend the concept of r and theta by introducing any other parameter? How? Let's say we are having this circular thing. Okay. Now, can we build up these circles and circles and circles and circles? And we know these circles have very medium thickness, so maybe we can have various amount of circles, one above and above and above and above, and make some height. And this height, we say that this is your x-axis, or this is your y-axis, and these guys are in z-axis. We take simple the circle which was in x and y, okay, but now something is interesting going on. This is z-axis. Now if you are taking this kind of thing, it will possess this cylindrical coordinate system, okay, because you know cylinder is made up of this concentric, not the piles of ring or piles of circles or disc, okay. This is called cylinder. So cylindrical coordinate system in three-dimensional space, which is represented by this r theta also, but with some z. And if you have any vector in cylindrical polar coordinate system, this vector will be represented by r hat, a theta hat, and plus az z hat. Well, if you follow this coordinate system, and if you have some kind of a wire, for an example, wire has very minimum thickness, but you can zoom in and you will see that there is a cylindrical symmetry there. And if you want to solve problem on this wire, you can use this cylindrical polar coordinate system to find out the volume, area, and so forth. For example, maybe electric field, or how much water is flowing through this pipe and so on. You can easily use this cylindrical coordinate system, and in less than 2 lines you can get the answer. So the symmetry, while using symmetry, it has the power of making our things very simple, okay. So we saw this cylindrical polar coordinate system, but what else in our magic box? Is there something we can think of more symmetrical? Well, we see raindrops, we see various things which has some more symmetry. For example, maybe r and theta, but it's not actually exceeding, maybe not piles of things, but yeah, it has some kind of a thing which is called sphere. We are seeing various objects which possesses this spherical symmetry, because our world is x, y, and z dimension, okay. So maybe I am using this here x for the convention purpose, y and z dimension here, okay. Now if I am having some object and it possesses this spherical symmetry, so instead of using a simple cubical thing, means that's a Eulerian thing, we can use this spherical polar coordinate system. Again, our main purpose is to simplify the calculations in a way that you cannot imagine, and if you have worked out somewhere, then you will see the power of this symmetrical coordinate system, that if you want to figure out the volume of this sphere using this spherical coordinate system, in a second, 1 or 2 line, you will get 4 by 3 pi r cube. That's the simple idea of this spherical polar coordinate system. So in spherical polar coordinate system, as we have studied that, yeah, we have this r because the radius is there. Again, it is making an angle something theta with z direction, okay. And then we have this phi, because again you can cut it out all the dishes and so on from here. So x and y is making the angle phi. So we have this y and g is making some angle theta, and x and y is making angle phi. So this x and y, which is making an angle phi, is involved in tracing the circles, and here theta gives you the rest of the part which can frame the whole spherical system. So our parameters are r, theta, and phi. So we had this system. So we figured out this Eulerian thing, x, y, z. And then we had this polar coordinate system in 2 dimensions, and we said that we don't live in 2-dimensional thing. So therefore we move to, can we add some extra dimension? and through extra dimension we see that cylindrical polar coordinate system, and then we saw this beautiful coordinate system about spherical symmetry. Okay, so let us move further and little bit dig deeper on this concept about vectors. That yeah, we have this vector